just for fun, let me show you how to start from this state 0, 0 and get to this state, which we call one of the Bell states, so you'll, or equivalently EPR state, EPR pair, or one of the 4 Bell states. Okay. This will be good practice with the rest of the postulates, really postulate 2, but working through some quantum circuits. So let's see how this goes. I'm going to start in the state 0, 0, and I'm going to draw you a quantum circuit, which I claim prepares the state. I'm going to do a Hadamard, which we've seen before, and then a new gate, which I'm going to call a CNOT gate, a controlled NOT gate. This is one of the exceptions where we do use an interesting symbol for, and I'll explain to you what it means. But my claim is that this will start in this circuit will map the state 0, 0 to this Bell state that you see here. And let's see how that works and get some practice working with the postulates. So again, whenever you're analyzing circuits, I encourage you to use the notation where you have this initial state you're in, you put an arrow whenever you apply a gate. And so what gate are we applying here? This is the first time we've analyzed a multi-qubit circuit. So you could say it's a Hadamard gate on the first qubit. That's totally fine. And I'm just going to be a little more explicit and write this as Hadamard acting on the first qubit, tensor identity acting on the second qubit. Okay. If there's no operation here, it's always equivalent to identity. So this means that I have to apply Hadamard to the qubit on the left and identity to the qubit on the right. Remember our definition, how we apply a tensor product of operators to a tensor product state. You do it on either side of the tensor product, right? So this is going to be equal to Hadamard 0, tensor identity 0. And recall that that's going to give us 0 plus 1 over the square root of 2, tensor 0. And now, in order to set myself up to do the CNOTs, I'm going to expand this state across the tensor product. You can put parentheses here if you'd like. So this is going to give me 0, 0 plus 1, 0 over the square root of 2. Now, this CNOT gate is going to have the following definition. It's our first time seeing it. You'll get very familiar with the CNOT gate. I'm going to define it to the symbol CNOT in the following way. It's going to be the projector onto ket 0, tensor identity, plus the projector onto ket 1, tensor, the poly X gates, poly NOT. Okay? What this means is that if the first qubit is in the state 0, you're going to do nothing. You're going to apply identity. Whereas if the first qubit is in the state 1, you're going to apply the NOT gate to the second qubit. You're going to flip it. Okay? It's an intuitive way to do it, but at least for today, I want to show you, all the steps to do this so that you could work it out for any 2-qubit gate, not just the CNOT gates. So let's see how that goes. Now I'm going to put an arrow, and I'm going to apply the CNOT gate. We're going to use several of our principles here. So the first one is going to be linearity. So I'm going to do CNOT to the first term, 0. Let me put back in the tensor products to be very clear. And then it's going to be over square root of 2 plus CNOT applied to 1, 0 over the square root of 2. Now I'm just going to use this definition. The CNOT has 2 terms itself. So this is going to be equal to projector onto the 0 state, tensor identity, plus projector onto the 1 state, tensor poly X, all acting on 0, tensor 0 over the square root of 2. And then the other one I'm going to leave you to work out for yourself. So I'll just summarize it, same line as before, CNOT acting on 1, tensor 0 over the square root of 2. Let's use linearity again. So again, I'm going to apply this sum of operators to a state. So linearity principle one more time. 0, 0 tensor identity applied to 0 tensor 0 plus outer product 1 tensor poly x applied to 0 tensor 0. The other term is hanging around for the ride, CNOT 1, 0 over root 2. Okay, so now I have to use our definition of what it means to apply the tensor product of operators to a tensor product of states. So this is going to be 0, 0 is the operator on the left of the tensor product. Ket 0 is the state, so I put a ket 0 here. And then tensor identity is the operator on the left, and then this 0, on the right, and then this 0 is the state on the right. Now I'm going to do the same thing for the second term. Plus 1, 1 is the operator on the left of the tensor product. Ket 0 is still the state on the left of the tensor product. Tensor poly x times ket 0. 1 over root 2 is still here. And then the second term is still along for the ride. So looking at this, the only thing to evaluate really is this inner product. Who could tell me what 0 inner product 0 is? Just 1. So this is going to be 1, and we're just going to have the state ket 0 here. And then identity acting on ket 0, I won't ask you. That's just going to be ket 0. How about the inner product of 1 with 0? 0, these are orthogonal. So this whole term is going to go away. Remember, if you have a coefficient in a tensor product, you could pull it out. Okay? So I'm going to have a coefficient of 0 here. So that means that this whole term is going to go to 0. Does everyone agree? So you see that after all that math, we see the obvious and expected thing, that we're just going to get still 0, 0 for the first term over root 2. And then try it as an exercise. Make sure you could go through all the math with this second term and see that in this case there is an effect. You'll get plus 1 tensor 1. The state of the second qubit will get flipped. The NOT gate will flip it, since the first one is in the 1 state, from 0 to ket 1. And that's indeed the final state that I wrote down here as the example of one of our entangled states, one of the 4 Bell pairs.